So this talk will be a little bit different than maybe some of the talks you've seen so far. Well, actually, I guess you did do quite a bit of live demoing in some of the previous talks. So this one's going to be entirely live, so I'm going to be doing some data analysis on some actual data that was given to me by Taylor Culver now. I don't know if he's around, but be sure to thank him later. Basically, I'm using someone else's data to do some analysis, and the first time I actually looked at this data in detail was last night. So in true grad student fashion, I procrastinated to the very end of this. So, but I want this to be one of those talks that the takeaway is, if you're in grad school and you're trying to do real work, find tools that help you to do the things you need to do quickly. Basically, find the things that really enable you to ask lots of questions in a very short period of time, because you don't know necessarily what will work. So you have to try lots of things, and some of those things hopefully will. And so with that, I'll dive into some of the tools that I use that I used when I worked for Oliver to analyze molecular dynamics simulations. Oliver's lab is a computational lab, so simulations of proteins is kind of the name of the game, trying to understand how these proteins do what they do. Who here is a computationalist? Raise your hands. Oh, okay, pretty much everyone. Okay, good. So this is at least relevant. I didn't know if there were some experimentalists that maybe are doing wet lab work. This might be a little bit less relevant for you if you were, but good. This should be great. Okay, so little point of introduction. So many of you probably do data analysis on your laptops. You may have access to a workstation that has your data locally. The data that I'm going to be using is on one of the file servers in the Beckstein Lab. So I'm going to go ahead and jump on that. And the data is stored in a place. Transporters, MHP1, in-house sims, and I lifted this data from Taylor's home directory, so I've sort of made a copy of it. What we've got here is a grand total of about 384 gigs of data, gigabytes. We won't be using all of it. The vast majority of that is going to be trajectory data, so positions versus time of atoms. So to give you an idea of what that looks like, here's a visualization of one of these simulations, at least the protein part. And what we're going to be doing is trying to obtain observables of this protein as it undergoes a conformational transition. So it's maybe a little hard to see with the rate at which this is moving, but if I manually run it back and forth, you can see that this protein, these two domains kind of come together, sort of sandwich some space in between. This transporter is called MHP1. It transports, I think it transports some larger ligands, but mainly sodium. Correct me if I'm wrong, Oliver.
It uses sodium to power the uptake
that's right.
of high-density and
yeah. So again, this is not my protein to study, but I am using the data for it, for this exercise. And so part of the mechanism, at least what we think is the mechanism, we haven't completely solved the mechanism for this protein yet, is that it goes from this inward-facing state where this bottom part is accessible to the inside of the cell. And if I draw, I'm going to go ahead and put the membrane back in. Let's see if we can't make this easy to see. Put in some points, and let's change the color. So this membrane, this protein actually sits inside of a membrane. So the full simulation box is a fully explicit, as in fully represented simulation box of waters as well as lipid molecules. So these form the cell membrane in which the protein sits. So this protein mediates transport of idantoin, and makes use of the sodium gradient across this membrane to power that transport. So understanding what that process looks like is our goal. Now, I'm not going to say that I'm going to solve it right here in front of you. This is just one piece of the puzzle, and using simulations like this can give us clues as to how the protein might transport molecules. So that's what the data looks like in terms of if we were to visualize it. It looks like this. But the way I'm going to analyze these results is not to necessarily visualize things, although that can be useful for certain applications, pulling this up in sort of a graphical environment and playing around with what's happening and actually getting a look at it. When you run 10, 20, 100, 1,000 simulations, you don't necessarily look at each one individually. You want to develop ways of asking questions of the data without manually looking at each piece. And so for that, a programming language such as Python is actually quite useful. You could scale out your analysis using that as well. So if we go back to the file system in which all this data actually lives, all of this, I'll give you a lay of the land. All of this, these trajectories that I'll be working with, you guys don't have access to the system, and that's perfectly fine. This is just me displaying something that you might have a similar case for yourself. You've got this file strewn about the file system. I've got all of my simulations inside of this directory here. Can everyone see this okay, or is it really dark? I'll try to make it a little easier to see.
That's worse.
That's much worse.
White, make it white background.
I think the lamp on that needs to be replaced. Do I have one? Yeah. That's better. Okay, we can work with that. So what I have in Taylor's data set is simulations in each of these numbered directories. So each one corresponds to one of those simulations in which we're watching this inward open state go into this occluded state. They're basically different runs of the same system, but with a different random seed. So the idea is we're not trying to run it once, we're trying to see if the behavior we are watching for is something that we consistently see throughout all the simulations. I should mention that these particular simulations are not equilibrium simulations, so they're not just putting the protein in there and then letting it go. They're actually forced to go a certain direction, but it's a bit of an entropic force and not a direct potential-based force. So the way this algorithm works, it's called dynamic importance sampling, is that we have a target structure, in this case, the experimentally obtained occluded structure. So this is my occluded structure, and this is my bottom open structure. And what we're doing is we're saying, this is where we're starting. We allow the simulation to proceed, and if it is moving, if it's proceeding in such a way that the RMSD between this structure, the root mean square deviation between this structure and that structure is getting smaller, then we allow it to go forward. If in a few steps it's going to move in a direction where the RMSD will increase, then we only allow it to go those steps with some probability. So in this case, we're sort of ratcheting the protein forward toward this target structure. So we might go a little bit back, we might go forward, but on average, we're going to move toward the target structure simply because we have this biasing. We allow it to move forward, but we only allow it to move backward with some probability. Now, you can argue that this algorithm may not necessarily produce the realistic transition, but it at least gives us something that it's a little bit better, or at least probably quite a bit better than interpolation between this structure and the structure where you're just morphing the coordinates. at least this has some real physics that kind of limit where it can go. And in fact, the protein is naturally reaching these places. It's just reaching places that it would take much longer with an equilibrium simulation to go. If we have a look inside of these directories, so things like directories like the 001 directory, this is the results of a single simulation. There's a lot of files in here. Who here does molecular dynamics simulations? Okay. Okay, cool. Have you used Charm? Who has used Charm? Okay, I've seen one hand. Charm's a pain in the ass to use. Can I say that?
Sure.
I'm not hurting anyone's feelings? Okay. If we have a look at the input file for this, is to telling Charm what to do. It looks kind of like this. It reads like Fortran, but even then isn't that pretty. Isn't quite as pretty. It's painful to use. But it does have versatility, and so that's why this algorithm was implemented in Charm, because Charm allows you to do lots of things like this. Charm also requires a lot of various files for setup. These are setup files from building the membrane in the first place. But the point is, each of these simulations, like this one, for example, has lots of files that together define the simulation that was run, right? Some of these files define the starting conditions of the simulation. Some of them define how the simulation should be executed, like that file we just looked at. Others are the results, like the trajectory. So this file right here happens to be the coordinate trajectory of the simulation. We have lots of files strewn about, and it's often a barrier to analysis having to run around the file system like I'm doing here and kind of pull everything together. Or if I write some analysis scripts, even with Python, if I'm hard coding a bunch of paths and just trying to keep everything organized in a way that everything still works, it's actually a bit tedious. So the tool I'm going to introduce is a tool I wrote during grad school simply because I would often run many simulations with different starting parameters, different choices of simulation parameters, and even different structures entirely. And after a while, I started to lose my mind a little bit, keeping track of what I had. So it became easier to deal with writing a Python library to make that easier. So with that, what I'm going to do is I'm going to switch into using a Jupyter Notebook. Show of hands, just so I know, how many people have used Jupyter before? Okay, good. So I won't belabor the point. I'm just going to start up a Jupyter Notebook in the stop level directory. And this is running on the file server upstairs. So if I want to actually get to it, I'm going to need to make an SSH tunnel. Points to that. And so here's my running Jupyter server. So this is running where the data lives. It's not running on my laptop. I'm just rendering it here. What I'd like to do is I'm going to make a new notebook, and we're just going to see where we can go. So what I'd like to do is import a couple libraries. One of these is Dashrant. We typically import that as DTR. What Dashrant is it's essentially a file system interface. And if you've ever used Python to do anything with dealing with lots of files in the file system, you've probably used os.path, for example, to string things together. If you've been a little bit more object-oriented, you probably used pathlib at some point, but that's fairly new. Dashrant is more oriented to people who have to trudge through a file system and are often doing it as part of data analysis. So usually scientific users, kind of like what this allows us to do is to take our file system and treat it in an object-oriented fashion. So I'm going to create an object called a tree. And actually I'm going to say run, this run directory. I'm going to refer to that as a tree. A tree is just a directory. So in Datrian parlance, we've got trees and we have leaves. Trees are directories, leaves are files. And if we wanted to, we could get the lay of the land here to see everything that's inside of root. You see that our file system has quite a lot of stuff in it. Using a library like this might be useful to make sense of it. We can do something like ask for the trees that are inside of that tree, such as P1 and P2. This gives back what's called a view, which this is a Datrian object that functions as an ordered set of trees and leaves. In this case, we have two trees. If I wanted to get internally the trees of these, I could actually dive further down. And if I was curious as to where these things live, then we could grab out the paths of these objects. We typically, when we're working with Datrian, we don't care too much about where things live. Sometimes you'll need to navigate downward to make use of things. And where I would like to go is, I would like to go into 4D1B. So this gives me back a tree because it's a directory, a real directory in the file system. And this is all of the directories inside of that directory. So all we're doing here so far is diving down into that file system that I was using a shell for earlier, but we're using Python library to do it instead. And we're just treating these things as objects. So I have simulations stored in these numerical directories, but I also have some other directories in here like incomplete, RST test, and target check, things I probably don't want. Because my goal here is I want to select out my simulations, because I want to analyze the resulting data from them. So something I could do is take this view and do a filter on it. So I could say, use a glowing filter. And that would get us only the numeric ones, for example. So I'm going to hold on to those. These are our sims. This is what we'd like to actually operate on. So if I write some code that needs to analyze each simulation, these would be the units of operation, these directories, since those are the simulation results, right? We can go a little further with Datrian. If I ever wanted to get back to this point where I've got my directories that are all simulations, I don't want to have to manually parse through things, I can create what are called tree ants out of each of these directories. So if I were to take this view, there's a method called a map method on it, which simply would apply a function to each of these things. I'm going to apply dtr.treeant to each one. And that would give me a list of tree ants, one for each directory. For clarity, I'm going to go ahead and do this as if I was looping through this. For sim and sims, all we did here was make a tree ant out of these steps. Now this did something special in the file system. If I go back to my shell, if I go down into run P1 4D1B and say 001 in here, there's a file that was created, not a file, but a directory called .datriant. This serves as a flag post. So by creating a tree ant out of these directories, we've marked it with this .datriant directory. Quick show of hands, how many people have used Git in this room? So Git does a similar thing, right? It marks a directory as a Git repository by sticking a .git directory inside of there. That's what distinguishes a Git repository from a directory that's simply its own. So that's what datrand does here. Inside of this directory at the moment is nothing. All we need is this .datrand directory, and suddenly this 001 directory is a treant. And you might ask, what's the point of that? Well, datrand now has a way of finding it. So if you were to call this discover function that's built into datrand, it can just find all of the treants that are defined in the directory below the current one. So we can get back what we've already created. Any questions so far? We haven't done anything interesting yet. Go ahead.
What is a treant, may I ask?
Oh yeah, okay. So a treant is a directory, but it has some special features. So let me grab one of these guys. So if I call discover here, I get back an ordered set of treants called a bundle, similar to a view. And I'm just going to extract out the very first treant that shows up in here, that's 001. I'm going to call it T. A treant is able to hold on to certain metadata. So in addition to having that flag post, that .datrand directory in there that serves to say, hey, I'm a treant, I'm special in some way, you can differentiate these things. So there's tags. Tags are strings that can be used to basically mark this treant as having certain features. So you can say, for example, I want this thing to be this is a dim simulation. It's MHP1. I'm just throwing. What's the
4D1B.
Thank you. I was going to get it from there. 4D1B. It's the 4D1B structure. And if I just do that, this guy has now the following tags attached to it. And these are stored within that .datrand directory. So they're persistent. What that means is if I open up a new Python session and I grab this treant later, it will still have its tags. In fact, if I open up multiple Python sessions, even on different machines that see the same file system, they will all see the same tags at the same time. So this is a way of actually giving some kind of persistent state to these directories that can be used for filtering them later.
And where does the name treant come from?
A treant is a walking, talking tree from Dungeons and Dragons. So basically, the idea is that it's a directory that has some special features to it. Not quite intelligent, but at least has a little bit more to it. We can take our bundle here that results from discover, and we could actually go ahead and just add a bunch of tags to all these guys if we wanted to. So in fact, I'm going to go ahead and do that. And that way they all have these same tags, because they are all repeats of the same simulation, just with a different random seed. So they're kind of samples of the same thing. I usually hold on to a bundle, just call it B. So we've got our bundle of sims, and they all have these tags. Now you could imagine that you might run some other simulations, maybe with a different starting structure, or maybe with a different protein, and you throw different tags at it. And say you sit down one day and you want to do some kind of analysis on a bunch of simulation data. You don't want to manually trudge through your file system looking for these things. Instead, you could just call discover at a directory way above where they all live, and then filter downward. So for example, if I take this treant T and I say tags.add, you're special. And I want to grab out the special treant, the one that has that special tag on it, from my bundle, And something I could do is I could say b.tags filter your special, and I would get back only those treants that match that tag, that possessed that particular tag. If there were many treants that have that, then I would get back only those. So if you look at the DatTreant docs, so if you Google, actually go to dattrient.org, click on documentation, there's a whole, quite a few different ways in which you can use tags to differentiate treants, and you can do not just say which treants have this, you can also say give me all treants that don't have this. So you can do negation, you can also do unions and say I want treants that have this tag and that tag, or treants that have this tag or that tag, or whole sets of them. So the purpose of tags is to give you handles by which you can grab onto only the things you're interested in at that given time, without having to do gymnastics in any script you write to say, I want the ones in this part of the file system, but not the ones in this. Yeah, Casey.
What's a symmetric difference?
A symmetric difference is where if you, so basically it says, if I have tags, some tags in here, and so if I have two sets of tags, it's almost better to think of it in terms of first it's just a difference. So if I have a set of tags, like a bunch of names, and I subtract off a set of tags for which some of them were present in here, then I would get the tags that weren't present in the second set. But a symmetric difference says take the difference of both directions, and then take the intersection of them. So basically find the tags that aren't present in either of the, or that aren't present in both sets. That's the simple way to say it.
So it's like the union minus the intersection?
Yeah, actually. Yeah. Yeah, exactly. So it's the union of those sets, and then you subtract out the intersection. Yeah. Because tags behave as sets, you can just sort of do these kind of operations on them too. So you can do that to get the tags you want, and then you could filter based on those tags. In addition to tags, there's also categories, and these are key value pairs. So if I have a treant, in addition to tags, it also has categories, which if you're familiar with Python, functions kind of like a dictionary. So it stores keys, and for each key it stores a value. So if I wanted to say, for example, that this protein is MHP1, I could store that category. And that would allow me to select out, if I had a whole bundle of these things, I could do group bys based on these categories. So if I, for example, I'm going to label one of them wrongly just for fun. Let's grab the second element of this bundle. That's treant number 2. And what we can do is we can say categories, protein. I'm just going to label it NHA, which is a different protein. And so now, if I took my bundle, I could have a look at the categories that are present among any of the elements in here. So there's protein. The first one, the 0th element has MHP1 as the value. The second element, or the first element, has NHA, and the rest of them actually don't have that category at all. And what I can do with that is I can say group by protein. This would actually get me back a dictionary that has values or keys corresponding to the values of protein present in the bundle, like MHP1 and NHA, and the values for each of those would be those treants that have those corresponding values. So it would allow you to basically say you studied multiple proteins over the course of your PhD. You had NHA, you had MHP1, you had a whole bunch of them, and they're all strewn out throughout the file system. you could grab up all of those triads and then say group by protein type, and then do different things with these triads depending on what protein they were. You could also fill in for categories other things like maybe what resolution the structure was, or what initial parameters were used for the simulation, what the time step was used for the simulation, which force field was used for it. Because you'll probably run lots of different simulations with lots of different parameter choices. And it's nice if you can just pull them all together and say, okay, separate by these parameter types, and then do some kind of analysis with them. Any questions on DATRAN, that stuff? That's pretty much the extent of DATRAN. That's all it is. It's a file system interface that features this metadata component that allows you to slice and dice directories based on their features. Okay, cool.
So how is this better than encoding things in file names? When I was a PhD student, my directories were protein / GROMACS / charm force field / 2 frames per second times that blah blah blah.
Well, the where this is better is that you can keep expanding this and without breaking anything. The trouble with I often did the whole nest things based on what it is, because you kind of have to do that to some extent to keep your sanity. I guess you don't have to necessarily, but most people have some kind of organizational scheme, and that's good. But oftentimes there's way more parameters than you could possibly encode in half. And you probably don't want to have paths that are 100 elements long simply because you said it's this protein with this force field with this time step with this choice of who knows what else, barostat, this choice of, it just gets tedious. Instead, you could encode all of that information, or at least some of it, inside of a dictionary, a key value store, kind of like categories. And maybe some of it makes sense as just labels, like the tags. You can just use these things later. Often you also don't know what's important until you're knee-deep in your research anyway. So it might be that the most interesting thing about your whole study is that you have different force fields you're using. And maybe that's the thing you're interested in, is how do these force fields differ in the results they get? Whereas for a different person, they might be interested in what choice of mutation is made in proteins. How is that different? How does that change things? So, does that answer your question, Henry?
Then I don't have to parse sort of paths and so on. I think another thing is that you often sort of work on one project and then you work on another one, and then later you realize you actually want to analyze all these data together, and they don't follow the same kind of path name convention that would allow you to sanely parse them. So, but if you can store your metadata, then you can just discover everything and then
sort out the dev, basically. Yeah, exactly. Yeah. I know my organization scheme changed over the course of 6 years. So when I was a first-year grad student, it was very different than by the time I was finished. So if I relied on how I organized things, then if I needed to go trudge through 4-year-old data, then I was in for a treat. All right. So let's actually use this stuff for something. So far, we've just talked about what it could be useful for. So I've got this bundle. Each of these things is a simulation. It's a directory full of data. What I'd like to do with it is I'd like to use a library called MDAnalysis to parse out the MD data itself. Quick show of hands while I'm scrolling through my cheat sheet. Quick show of hands, how many people have used MDAnalysis? Okay, cool. How many people have heard of it? Okay, well, you've heard of it now, so that's fine. We're going to make use of it. So as a quick demo of what MDAnalysis allows us to do, if I import MDAnalysis as MDA, which is, as is the custom, I can create what's called a universe object. for the simulation. The way to think about a universe is that if we go back to our VMD example here, everything in here is the universe. So it's all of the atoms, it's all of their positions with time, so it's the trajectory data as well. It may even be velocity data. It could also be force data. Basically, it's everything that corresponds to the simulation data. Usually the way you create a universe is by feeding in a file that gives you the topology information, so names of the atoms, which residues they correspond to, which protein or which structure they correspond to. For us, that would be something like, if we have a look inside of this simulation here, that would be something like this guy. Nope, hold on. Last frame 0, that's 0. So it just so happens that this happens to be the starting structure for this simulation. And we're going to use that as our topology. So it defines everything in the system.
There should also be a PSF file somewhere that you can use.
Let's see.
So it's the same choice.
Right here, bold included.
Yeah, if it loads, fine. So it has more
It's also this one.
Oh yeah, set 5 assembly. I think it's probably the one.
We'll use that one then. That works. So we need something to define the topology. That is the identity of everything. So what I can do, since I don't really want to hard code a path here, is I could take my tree ant and I could select this file. This is a leaf, step 5 assembly.psf, and I could use that as my input. If I wanted an actual path that is a string that tells me where this thing lives, because we have to feed that to something we'll use, we could do this. Likewise, we could get an absolute path a similar way. For us, the relative path will work just fine. So this is my topology. We also need a trajectory file if we want to do some kind of trajectory analysis. So if we go back to the straw output, it turns out the trajectory file for this simulation is this guy right here, this DCD file. So I'm going to take that, similar fashion. So that would get us this file. So we can feed this directly into the universe constructor to build a universe object from the system. It takes a little second because first the topology file has to be parsed, and if it's rather big, it might take a few seconds. So this universe has 79,012 atoms in it, all told, so it's a decent size. What we're interested in is only a subset of that, though. The kind of analysis I'm going to do today is just going to concern the protein. Remember that this simulation system includes water. It also includes a membrane. So all of those atoms there, that's actually the lion's share of the box. Yeah?
How specific is MDAnalysis to having atoms? We do coarse grain simulations. Will it accept those, or will it freak out for not having carbon atoms?
That's a good question. So it turns out one of our core developers, Richard, I think has never done protein simulations in his life, and yet this library is kind of built around that. Mm-hmm. He's done most of the coarse grain kind of polymer stuff. So the answer is yes. Cool. Yeah. And if we have a look at the docs, so mdanalysis.org will take you to such limited resolution website this one's part of. You can have a look directly at the docs. The developer community is very involved. They're very active. There's a lot of there are a lot of coordinates module, or a lot of coordinate files that are supported. So I don't know which what kind of files you guys typically work with.
We probably write our own because we have a development.
Okay, yeah, it's possible to actually write your own parsers to feed into the system. So you can at least take advantage of all that's already there. In fact, some of these, like the XYZ trajectory reader, the XYZ format is like probably one of the simplest text-based. It's basically XYZ coordinates in a text file going downward over time. So it's very hackable in terms of developing your own readers. So if I have this universe, I can begin to sub-select pieces out of it. So often when I'm interested in all the atoms, we're interested in selections of atoms. So we might be interested in just the protein. Or we might be interested in taking a selection of the atoms and then comparing it with another part of the system, or getting distances between different atoms in the system. The way to get at that then is to use, or rather the first port of entry kind of for this is the select atoms method of the universe, which allows you to say something like protein, and that would just get you protein atoms. If you wanted only the C alphas, that is the atoms that had name CA, you could do this. If you wanted, there's probably not any hydrogens, but if you do H star, it'll get you H1s, H2s, or any HBs, and so on, which you often find here and there. Any other interesting selections that you can think of?
Volatives? Volative.
Yeah. So there are some. Is there not a preset for that one? Okay.
Probably race name Sol.
That's right.
No, race name HOH.
Probably for the DCD or for the PSFs. Something we could do is I could take my top file and let's read the first 1,000 bytes from it. Oops. It's a path. Just do this. And waters would probably be pretty far down, unfortunately. So.
But you could do u.atoms, race names.
Ah, that's true. So, given that we may not know exactly what the names that are in here are, exactly until at this point, I could actually access an atom group of all the atoms in the system. So instead of trying to select from the universe itself, I can get an atom group that contains all these atoms. And then we can call different methods on this. So there's methods like charges, which you can call this. This would actually get you a NumPy array of all the charges of every atom in the system in order. So PSF file has charge information. This would give you that information. Likewise, it has a names array. So this is every atom name in the whole system. There's also res names, which is likewise the residue names attached to each one. And if I wanted to see kind of what's there, why not?
Why don't you make it a set?
Let's do that, thank you. So if I make it a set, we'll get rid of repeats and we'll see what's present. That's a very good suggestion. And it looks like we have, it's probably, Tip 3P, yeah, because these are Tip 3P waters. So we can use that to select the waters in this case. These res names and all that, that's built on from the contents of the file. So whatever's in there, whatever your waters happen to be named, that's what's going to show up here. So to your question about can I use a custom file format, yeah, if you write a parser for that, then you can fill in the appropriate things from that. And that way, the universe has all the information it's present.
So as long as you have particles, you can make it work.
Awesome.
It was just tip 3.
Tip 3. So that would get us all our waters. We can also do, like if I wanted only the hydrogens from waters, then I could do this. Say, get me all atoms that have res name tip 3, and then have name H something. So that would give me all the water hydrogens. Likewise, this would give me all the water oxygens. Yeah, OH2, OH2, yeah. It's also possible to access position information. So let's just grab, for example, I'm going to select things in a different way this time. So if you've ever used NumPy, quick show of hands, has anybody here used NumPy? Yeah, good. So for NumPy, if you've ever created an array of values, so if I create this array here, it has numbers going from 0 to 99, I could say, get me only those values that are equal to 21, and that would select out those values. So it uses what's called Boolean indexing. In the same sense, we can do Boolean indexing on, for example, this names NumPy array. It has all these names in it to select out only those atoms that have name CA. So this is an alternative to doing something like u.atoms.select name CA. Same idea, but sometimes one form is actually easier to use than the other. I'm going to select out, let's see. What I'd like to do is, I'd like to do an analysis where I calculate the RMSD with time. And to get to that point first, let me talk about, I have this atom group of C alphas. In addition to all these attributes like names, things like mass, and charge, and things like this, we can also access positions. So if I say C alphas dot positions, then that gets me back a NumPy array that gives me the three-dimensional position of each of these atoms. So it's going to have the shape of number of atoms 3. And this attribute will change values depending on which frame we're looking at, the trajectory. If we look at u.trajectory, this gives us what's called our reader object, which points at this DCD file that we gave it at the very beginning. This file has 796 frames, and currently, if we ask which frame we're on frame 0. But it's possible to change the frame. For example, let's switch to frame 10. And so now, if we look at CAS.positions, these position values will be different. That's because the positions attribute will reflect the current state of the trajectory reader. So the way MDAnalysis behaves is a little different than perhaps some other libraries out there. If we have our trajectory, this is t equals 0. So we'll say t equals 100, where this is maybe a frame number. Initially, when we create a universe, this will point right here, but we may change that, just like I did there, where I switch the frame to point somewhere like t equals 10. And in that case, the positions of an atom group, such as CAS, the one that's all C alphas, that will reflect whatever the positions are of that atom group at this frame. So the reason I'm pointing this out is it's a bit of a different behavior than sometimes people expect when they use MDAnalysis. So it's actually quite handy, though, because MDAnalysis only reads one frame at a time. So even if you have a symmetric trajectory that's hundreds of gigabytes long, you don't have to load that all into memory at once. You're only loading one frame at a time. And this affords us a lot of flexibility because if I wanted to analyze not one simulation, but maybe 30 simulations at the same time, and I have 30 cores available, I could actually walk through all trajectories at once and not worry about running out of memory. The thing I probably worry about at that point is disk speed, I/O speed, but at least I won't be filling the machine's memory with coordinates. So, with that, let's do a quick plot of... I'm going to create a figure just to show kind of how we typically walk through a trajectory, and then we'll do some more advanced examples here. So, if I were to say for TS, that is for time step in u.trajectory, where initially I'm going to set u.trajectory to 0th frame. So now I reset it to the very beginning. Let's do CAS dot center of mass. I'm just going to record the center of mass, and I'm going to append this to a list. So we'll walk through the trajectory, and now we've obtained this list of centers of masses. Notice how it's different. We've asked for the same thing, CAS dot center of mass each time, but notice that each of these arrays has different values in it. We created a list of NumPy arrays. They each have 3 elements. It's a 3-dimensional center of mass. Any questions on sort of the functionality here? Any concerns as to like your own projects, things you might be doing, whether or not this will work? Something we might do is get a distance between 2 atoms or 2 residues. There are 2 residues of interest in this protein. I think it's tryptophan 117 and tryptophan 220. Does that ring a bell?
Could be, yeah. I don't remember the exact number.
Let's look at the literature. 117. Yep, there it is. 117 and 220. Yep. So these 2 residues, if we have a look at them in our structure, let's get rid of all these points. Res ID 117.
Pretty sure it should be an or.
Oh, thank you. Thank you. That would not work.
It's also turned off, isn't it?
It is. Thank you. So there's our tryptophans, right there in the middle of the protein. So it turns out that these tend to sandwich the ligand as it binds. We might be interested in getting the distance between these with time, because as we see in our simulation, they start out kind of spread out, and then sort of get a little bit closer. Maybe in some simulations they get closer than in others. But we could at least quantify this. So the way I want to do this is I'm going to write a little bit of code that grabs, in this case probably for tryptophan, which atom you would probably want to use as a reference, maybe just the center mass of the array or something.
Yeah, center mass of the side chains, I guess.
To do that. So let's select each of those tryptophans. So for this one simulation, we're going to select off tryptophan 117, select 222, and then we'll get the distance between the side chain center masses. So first, TRP 117. If I have my simulation, we can say select atoms, protein and res ID 117. Let's do a quick sanity check to make sure that's actually a tryptophan, because it's often the case that for structures, the numbering that's in a published structure may not match what's in your starting structure for your simulation. So it depends on how you set things up. This is going to be an atom group with a single residue. You might be asking, why does it say tryptophan many times? It's because this is a single tryptophan residue. This is an atom group comprising all the atoms in that residue. And so this is giving the res name corresponding to each atom. MDAnalysis does have a concept of residues. It has 3 levels of organization built into it. So it has atoms, it has residues, and then on top of that it has segments. If I wanted to take this atom group and get residues out of it, I could call residues, and that would give me back a residue group with all the residues represented in that atom group. And it turns out there's just one. And it's this 117, and it's a tryptophan. So we managed to select out the atom group corresponding to this tryptophan. We also want TRP220, so we'll select that guy out too. Oops. So we've got our second one here. So we might want to ask now, okay, we only want to get the side chain, we don't want the backbone. So if I have this atom group, I might want to select out only the atoms that are part of the side chain. The way I can do that is I could actually call select atoms on an atom group, and I could do something like not backbone. And that will effectively filter out the atoms that were part of the backbone and give me only those that are not. So I'm going to call this TRP220 sidechain, SC. And likewise, I'm going to do a similar thing for 117. We'll see how we can make this a lot more useful. What we're doing right now is we're prototyping an analysis by kind of throwing things around the notebook. In a second, we'll see how we can draw this together to create a single function that we could apply across all these simulations. And we'll do it in a way that it's actually pretty quick. So we can make use of parallelization, just as a sense of where we're going. So I've got these 2 side chains now. Let me call the center of mass on this one. So this is our center of mass. If I want to take the distance between these 2 side chains, I could subtract these 2 vectors, and then I could get the absolute value of them. And that would give me the distance, right? So I'm going to take the center of mass of this guy. And then I think there's like a NP dot.
NP.lim out
That's
one.
Yeah, it's that one.
Cool. So that would give us that distance between them at this point in time. So we'll have to ask ourselves the question, which frame is our trajectory on? Well, currently it's on frame 0. So this is the starting configuration for the simulation. Let's get this distance for every frame in the system. So every frame in the whole trajectory, starting from 0 all the way to the end. The way we can do this is to do a loop like we did before. So for TS in u.trajectory, we're going to do something like this. And I'm going to create a list of these things. We're just going to append all these together. It's kind of a quick and dirty way of getting this information. So we got it. This would be our distances with time. So it looks like it mostly fluctuates, but maybe decreases a little bit from where it started. We could plot this to be a little bit more systematic about this. We'll import matplotlib for that. And so this would be at least a first stab at getting distance with time between those centers of masses of each of these residues. Cool. Now what if we wanted to get the same data for all of them, all of our simulations? We could manually run this notebook again, but select a different one each time. But that would be tedious and awkward. We've written all the pieces we need to do exactly what we want to do, just run this on all of them. So let's go ahead and use those pieces to make ourselves a function we can apply to each one, and we'll see how easily we can do it.
Can I ask for this being plotted over the actual time that you can get from the time steps? So I can make
Let's do that. So what I didn't record in here was time. Let's hold on to those times. In fact, what I would do is make this it's just times. We can access the time information from ts.time. So ts is the time. What is it?
time step.
The time step. Basically, it's a time step object. It just references the current step that we're on. So if I get ts.time, if I record that, then I'll have all my times. Times now looks like this. It's often the case to use a library that's good for time series data. We're going to use pandas for that. How many people in this room have used pandas before? Okay, good. So this is something new. This talk is a bit of a whirlwind tour of things that might be useful to you, so it's mostly to give yourself a bookmark in your head, things you might want to look into further. Pandas is useful for time series data. It's useful for tabular data, time series being a bit of a subset of that. What we're going to do is we're going to create what's called a pandas series object. And I'm going to say, feed it the distances, and then I'm going to set its index to be the times recorded. This would be a pandas series. So I'm going to rename distances to that. And now I could actually use this series object directly to make a plot. So on the x-axis will be those times, and on the y-axis will be our distances. So that's our first stab at this. Any questions? Yeah.
Could you please explain what's TS?
Okay, yeah. So TS.
No, I mean, could you scroll up?
Yeah. This guy right here. So what TS represents, TS is what's called a time step object. If we iterate through a trajectory object, or a reader, trajectory reader, then what it gives back is this time step object that simply references the current frame. So it has information like the frame number, that it is the time. It also has, I think, positions information for all the atoms in the system. It has access to all these things directly because those are actually stored in the trajectory file, which it's built from. Does that answer your question?
Yes.
Cool. So let's take everything we wrote, put it in a form that we can easily apply it to 100 simulations at once. So the way we're going to do that is we're going to write a function. So I'm going to say get TRP distances. And what I want this to take is a sim. I want to feed it a single directory that represents the entire simulation. And what does this thing have to do? Well, if I scroll up, I'm going to just give to myself all the things I need by stealing from past me. We're going to just take this top file, and instead of B0, this is now going to be just taking that sim and extracting this PSF file from it. In a similar sense, we're going to have this Traj file, which I forget what that was. It happens to be this name for all of these simulations. Now we can create a universe using the top file and the Traj file. And then we can make our atom groups. So remember, when we're writing this function, we're sort of starting from scratch. We're saying for this sim, do the following things. So I'm going to create TRP220. And I'm going to simplify it further. Instead of creating the atom group and then subsetting that, I'm going to say and not backbone right here in the selection. Because by putting that in there, we're already going to filter down to atoms that aren't part of the backbone. And we'll do the same for 117. We're almost there. Now, what do we want to do? We want to actually iterate through the trajectory. So for TS in u.trajectory, we will get that center of mass difference. So we'll do the same thing we did above. We'll create this distances list. We'll create a list of times. We'll also append the times, so we can hold on to those. And what I'd like to return at the end of this function is this data packaged in a nice form. And so a nice form for this kind of data, this time series data, is to stick it in a series, a pandas series. We'll stick it in series using the times as the index. So that's my function. So now I could do something like get TRP distances B0. And that will do all the work that we just did in all those cells, just about. We did it all kind of manually to figure it out, figure out what we wanted. And now we can kind of just apply it to any of these sims on demand. Since each element in this bundle is a different sim, we can just keep feeding it. We don't want to do that manually, though. We could just loop through it, but at this point, these are all separate things we could do, right? Each of these simulations is independent of the other, and so, in fact, if I have a machine with multiple processors on it, I might as well make use of them. So, it turns out that since we wrote this nice function that takes a sim as input, we can take advantage of our bundle. It has this map method, which allows you to apply a function to each member of the bundle, perhaps in parallel if you want. So we'll go ahead and use that and get some output back. So we're going to get back all of the results at once. We're going to call get TRP distances on the bundle, and we're going to say we want to use 10 processes. Happen to know the machine that I'm using. Really? This machine has like 10 cores or 12 cores on it. So this is YamSolo's view of this file server. It has 12 physical cores And so I know that I could probably get away with using 10 processes that'll run at the same time, and the rest of the machine stuff still run with that issue. So we'll go ahead and use that. We'll hit execute. We'll see if the machine gets real busy real fast. So now we're just waiting for our results. We're going to run through all the simulations. We might have some issues because it turns out that of these 50 sim directories, only 30 of them actually have usable data in them. And so we'll see how we can handle some errors. Looks like it's finished. That's because we got some exceptions. Oh, but it seems like it went cleanly anyway, so let's see what we got from distances. Oh, it failed, okay. This is distances from when we used it previously, didn't get reset. What we need to do is add some error handling to this function, because it turns out for some of these simulations, for example, if I say grab the last one here, we're going to get an OS error because this particular directory doesn't have a DCD file that is finished yet. It's actually either corrupted or half-written or something like this. So to account for this, the fact that when you're dealing with lots of data, especially lots of simulations, some of it might have issues. You might want to write functions that can handle it. We're going to use a bit of a blunt instrument here and just say try to create the universe. And if you fail in whatever way, then just return none. So say, you know what, I don't care. We don't need that data. If you're actually writing this, you might really want to figure out what's wrong with your simulation data and not just write code that says ignore issues. But for our purposes, we're going to just ignore problems. Pretend they're not a thing. So I'm going to rerun that map function. This time it should just be able to bypass any of those issues and say, well, who cares? Yum Solo is busy. And now we just wait. But it turns out mapping a function to lots of individual things is a pretty common thing, right? It's often the case that you'll run several repeats of the same simulation. It's often the case that you'll have several samples of the same, in principle, the same thing. You kind of just want to execute some function on all of it to get the results back, and you can do statistics on it. So now we have our distances. This is a big list of series objects. I'd actually like to turn this into a single series object. So I can do that actually by taking our bundle, grabbing the names here, and I'm going to do something like, say, sim.name distance for sim distance. We're just going to iterate through both the names for both the sims and our series objects and get back a dictionary. And pandas allows us to concatenate these things together to create a single series object that has multiple indices. So all of these times and all of these distances for each of those times correspond to simulation 001. All of these correspond to simulation 029. So we're kind of aggregating all of the data from all 29 of these simulations that actually finished. And I can tell it what names to use for these. I'm going to reassign distances to do this. So now, we're really cooking with gas, because we've got everything in the data structure that we can easily do statistics with.
Can you name the other columns?
Yes.
As well, I don't know, time and distance or something like this?
Yeah, so something I could do for that is, I'm going to go further up. What I should have done is named it here. So what I'll do is I'll actually go ahead and rerun this. It's the easiest thing here is just to edit what I've done, and in this case rerun it. Set s.name to be distance. Set the series to have a name. and then return that series in the end. It doesn't take that long to run this, so we're just going to rerun it. So it's hitting those errors, but because I told it to ignore the exception, I basically said, okay, if something happens, move on. It's passing right through it. Okay. So we can get our distances back, and now we've got sorry, s stop name, and then we wanted s stop index to be named to be time. So a series is an object that has, think of it like a NumPy array that's one-dimensional, but in addition to the values themselves, it also has an index that can be floats, for example, it can be times, kind of like how we have here. They're labels. And so what I'm saying is I want to call the index time, the series itself distance, and this outer index that I created called the sim name itself. And the reason why it's useful to kind of go through this to put the structure in place is it makes it very easy to plot. It makes it very easy to also produce summary statistics on the basis of simulation or on the basis of just times and aggregating across that. So if I pull those all together, now we see that our series has this first index is sim name, the second index is time, and the whole thing's called distance. It's okay. And I can go ahead and plot this. If I plot it right now, it's going to be really ugly. But if I do something like distances grouped by sometimes it's easier to split these guys back out. I remember this. So what we'd like to do is plot each of these simulations results on one figure. And so if I create a figure object with matplotlib, I do something like plt.figure, and then create an axis that corresponds to that. Then we could loop through each of these groupings in the series. Should be able to.
It's subplot on subplots.
Well, maybe not. Maybe not so. In principle, we can pull all these things together and make use of them as one unit. I think what I'll do is use a data frame instead, just for one index, because that's a little easier to work with. So we could make this a data frame. We can actually just do as df. There we go. So pandas includes two main objects. There's a series object, which is just a one-dimensional series of data sets or data points, so like distances, for example. But there's also a data frame object, which can include multiple columns. In this case, we have a data frame with just a single column, but often a data frame is a little easier to work with because that's kind of what we typically use pandas for. And so if I do what's called a group by, say on, I think I can do by name these days. Yeah. Then we could, for example, get the mean value as a function of sim name. So if I wanted the mean distance for each simulation between these tryptophans, then I could say for each simulation that is grouping all of the rows by simulation name, take the mean and then give me that result. Yeah.
They all have the same value. That looks fishy.
Ooh, good. That does look fishy. Let's go back to our original time series. We probably weren't very careful with copying and pasting stuff in here. Something we can do. Let's have a look at if we get the same values for each of these. So if I get the same result for calling get TRP distances on 0, 1. Ah, okay. Yeah, we get the same result for every single time.
We never set trip 220 underscore SC.
Yeah, you're using. Yeah.
Ah, thank you. What it's doing is when I run this function, it's actually grabbing the one that we defined way out further in the notebook. Due to Python scope rules, it finds that name, TRP220 underscore SC way up there, and uses those values. So we're getting exactly the same result each time. So thank you for catching that. If we fix this function, now we should see that we get different values for each of these times. Because it's actually pulling the right position now with the change in time.
That also explains your funny plots.
That also explains the really stupid plots that I was struggling to understand. Okay. Which means they were probably fine. I was just looking at the wrong problem. But that's okay. That's kind of the nature of doing science this way, is that you'll notice something, you'll try to go figure out what's going on, and eventually you hit a point where you realize that there is something funny going on, you're just looking at the wrong thing. So let's rerun this. Fortunately, the value of putting things in code like this, of analyzing data with something like Python, is we could find the fix and then just rerun everything. It took us like 2 seconds, instead of having to manually maybe go through BMD and measure stuff again. Of course, you could argue that if we weren't writing code, then maybe we wouldn't have made that particular mistake. But even so, I still say it's the better solution. So now our means are very different. And in fact, if I go down here and try to do this with not if I try to make a series out of this, it probably would be fine. Let's call distances.plot. That's a little bit better. Although that's all of the distances with time. So if we wanted to do something like that, gets us what I was trying to go for, which looks a little bit like modern art, but that is all of the time series, all 30 of them plotted on one figure. So you see, at least there's a lot of variation there. Yeah.
Do you have to group by the first thing, or could you group by time or distance if you wanted to?
So if I group by time, that's a good question. We'll see what that result looks like. One, we could just run it, so let's just try it. It's taking forever because that's a lot of groups. It's going to look like that. What that's going to give us is, instead of a line for each simulation, it's going to give us a line for each time value.
I like this one better.
Well, it's pretty too, but it doesn't mean anything. But we can see the effect of doing a group by, for example, with this mean. So if I chose my level, so if this is my data frame, where I have sim name and time as my indices, I could do group by level equals time. And if I call mean on that, what we're going to get is the mean distance corresponding to that time across all simulations. So you're averaging together the distance that was present for time 0.5 across all 30 simulations.
Can you plot this now?
Sure. So now if we call down the bottom of that series, we get something like that. So that's actually kind of cool, because that does tell you the mean trajectory that these things took. And in fact, you could also get error bars on this. So if we were to do the group by, same kind of group by, and get something like SEM, so standard error of the mean. Let me hold on to this. Let's see. I think I should be able to do Y error. Cross your fingers. It's hard to see those error bars because there's so many of them. Let's make a bigger figure. Should you go big?
Can you just like set the X limit to
let's do that.
a couple?
Let's go 0 to 10 or something. There you go. Maybe 0 to 100. Yeah, so this is basically the average trajectory taken by that distance between those two true events, the average distance across all simulations with time, which is actually kind of a cool thing to have a look at. If we go to 1,000, then of course it looks kind of like that. Any questions on the stuff I did? I know I threw a lot out there at once, but that's kind of the nature of working with a programming language like Python to analyze data, is you'll pull together these various packages to do different things. So at the beginning of this talk, we used Datrian to kind of explore our file system, grab up the things we're interested in from that file system, and then we used MDAnalysis to take specific files for each simulation, load them up in a way that we could use them. So grabbing out different atoms, sets of atoms, calculating some observable from them, doing that through the whole trajectory. And then we went back to using Datrian and said, I want to apply this operation, this making a universe object, grabbing these atoms, getting some observable. I want to apply that on each of them. And we were able to get that done in parallel. The results we took from that, we then took yet another package, pandas, stuck them into a data frame, and now we can do analysis on just that observable. And we can do all kinds of fun things with it in combination with MATLAB. There are many libraries out there that there's no way I can possibly cover in the span of what we've used today. But this is just sort of a sampling of what you could do. MDAnalysis also features some built-in analysis libraries. I was going to do some of those examples, but I don't think I'm going to, unless people want to stick around. There's actually some cool examples in here. But there's a lot of pre-built stuff for those of you who use MD. So if you're interested in those, we can actually have a look at what's on offer. What's the word analysis is everywhere?
It's 4.
Oh, thank you. All right. I tried searching for the word analysis on the MDAnalysis docs. Obviously, it didn't help me get anywhere. So this module contains all kinds of sub-modules for specific things. For example, doing an alignment of a structure against another structure. So by minimizing the RMSD between them. So you might do that if you were trying to get some kind of measurements between frames of the same trajectory. There's distances and contacts, fitting and alignment, native contacts, distance analysis, path similarity. There's also hydrogen bonding. I was going to do one of these examples. We could do it if people are interested. It doesn't take too much time. There's some membrane protein specific stuff. And if you're doing DNA, nucleic acid things like nucleic acid bending and shearing, things like that, how these base pairs align. There are some bigger structural things like elastic network analysis. There's volume-related analyses and some other stuff. So MDAnalysis, in addition to providing some general-purpose pieces like the universe object that allows you to pull data in, atom groups, residue groups, trajectory readers, it also features some applications of those, at least for some common things, or maybe some things that are less common, but some starting points for those. I think I will go ahead and do that little each box analysis.
So how about we'll sort of say we'll do questions and answers yet, and then if anyone wants to stick around, then I would love to hear more about sort of the specific application. So.
Okay, cool. Yeah. Any questions? Otherwise, yeah.
One general question. So is it possible to visualize your system using MDAnalysis?
So MDAnalysis doesn't include built-in visualization, but there's a library called NGLView. It's a Python package that does allow you to visualize directly in a Jupyter notebook protein structures. I haven't used it in quite some time.
Can you try it? It should work.
Let's try it.
I've tried it recently.
So what I'm going to do is I'm going to try to install this. So it's called NGLView. So if you were to install that, I don't know if you have to register the widget and all that stuff.
I think it works, but you'll have to restart your notebook.
Okay, I can try that.
Probably you have to...
Let's just try it first. So if I do import NGLView as NGMV, the imports, it includes a...
I think it's show MDAnalysis.
That's it. It includes some convenience functions for some commonly used packages, including MDAnalysis. If we look at what the docs for this say, it says feed me an atom group, basically. We can also take a universe. Let's go ahead and feed it
select atoms protein.
Yeah, let's just grab the protein. Because if we feed the whole system into it, it's going to be kind of, it's doing this all in JavaScript, so it's not big. But it can do it. It's just unwieldy.
I think you have to assign it to W or something.
That's fine.
You didn't cross your fingers fast.
So if everything worked, it would show a widget.
Yeah. So the notebook, you usually have to register widgets beforehand or something like this. So you might have to play around with it. I would have a look at the NGLView docs. NGLViewer. So what it looks like in the notebook is actually like this. So it's actually quite slick. So that would allow you to go from, instead of having to switch to like VMD and then go back to a Python session, you could actually do full analysis, including visualization, directly in the same notebook if you wanted to. In the past, I've done that. So yeah, so I would have a look at those docs. It's a pretty cool little package. Does that answer your question? Okay. If there's no further questions, thank you guys for listening to me talk at you for an hour and a half. Hopefully this was at least useful to you. Hopefully it gives you something to walk away with. I'll stick around for questions. least until probably, it's planned to be here till 4, so we want to ask for individual things. Thank you.
So could we share your notebook?
Sure. Yeah, I can stick it somewhere. Do you want? Are you okay with me sharing that?
Yeah, sure.
Yeah.